Okay, now let's do a couple of examples. So let's say, let me call it example 1. I have a block tied to a spring of a spring constant K, and this is mass M. Okay, and I'm going to compress this spring. So let's say this is the no stretch position, or we could also call it neutral configuration. So from the neutral configuration, I'm going to compress this spring by a certain amount. So the block is here. Let's say I compress it by an amount of, I don't know, we'll call it, let's say 1 centimeter. Okay. And then, of course, when I compress it, the spring is going to compress. And because of that configuration, the spring is going to store some energy in it. And that energy stored, as you can guess, would be the potential energy due to linear elastic forces. So we can compute what that would be. So let's say K is given to you as, we'll call it 10 Newton per meter. We know that should be the unit because F is equal to K times X. So this is in Newton, this is in meters. So K, the unit of K would be Newton per meter. And then I let it go. So this is a position, we'll call it position 1. And so in position 1, I let it go, which means that I release it from rest. The question is, when it reaches this no stretch configuration, the neutral configuration, let's call that position 2. In position 2, what is the velocity of the particle? Okay, so we know that it will acquire some velocity when it gets to the position 2. So then the question is, what is that velocity? So to solve these kinds of problems, the first thing you have to do is apply a systematic way of looking at whether this problem can be solved using the work energy approach or not. Okay, so let me first give you a process for solving this problem, or we'll call it procedure. Okay, so procedure. So procedure starts with a test. So the test is that you have a finite displacement scenario. So finite displacement. Okay. And you have to relate velocities with displacement. Okay, so that's the test. So if the question says that you have something in one position and goes to another position, and the question is only asking you to relate the velocities with the displacement, it's not asking for acceleration, that's the main point, then the test for applying the procedure from the work energy approach would be applicable. So clearly that's the case over here. We have a finite displacement, we have position 1, we have position 2, and we are being asked to relate the velocities. In position 1, the velocity is 0 because we are releasing it from rest, and we're looking for the velocity after a certain distance it has traveled. Okay, so the test is positive. So the test is positive, then what you do is draw free body diagram in a generic configuration. So by generic configuration, I mean a configuration that is not special, wherein maybe a certain force might be 0. So in this case, for the particle tied to a spring, you might say the generic configuration is somewhere between 1 and 2, and you will draw a free body diagram. You will have the normal reaction from the ground, you'll have the gravity, and somewhere here it will be compressed, so you'll have the force Kx that way. Okay, so that's a free body diagram with generic configuration. Now notice that if you drew this free body diagram in position 2, you would not have any force from the spring, right? Because in this position, the spring would be unstretched. And that's why we say draw it in a generic configuration where you can potentially account for all kinds of forces acting on the system. So that's the second step. The third is to recognize conservative and non-conservative forces. Okay, so if all forces are conservative, then you can apply mechanical energy conservation principle. Okay, if not, then you go back to using your general work energy relationship, which is W equal to delta G. That's always valid. So now let's apply this procedure to this problem that we are solving. Okay, so we can see that in the free body diagram, N will not do any work, Mg will not do any work because they're perpendicular direction displacement. The only work done would be due to the spring forces. Okay, so We can definitely use W equal to delta T, but in this case, we can see from the step 4 that all the forces acting are conservative because Kx is a linear elastic force, which is conservative. So we will actually apply T1 plus U1 equal to T2 plus U2, conservation of mechanical energy principle. So what is the kinetic energy in position 1? It's 0 because we are releasing it from rest. Okay, what's U1? U1 in position 1 would be equal to 1/2 K times x1 square, where x1 would be the stretch or compression, and the compression over here is 1 centimeter. So that would be 1/2, K is 10, and x is 10 power minus 2 in meters, so that's square. So we get what? We get 10 power minus, this is 10 power minus 3 divided by 2. That will be the joule. So that's a very small quantity, right? That's U1. What is T2 in position 2? We don't know that. We'll call it 1/2 mv2 squared if the speed is v2. And what's U2? U2 in position 2 is 0 because we have reached the unstretched position, right? So essentially what we're saying is that initial mechanical energy was composed of only potential energy U1. That was the initial mechanical energy, and all of it was converted into the kinetic energy in position 2. Okay, so all we have to do is equate those two. So T1 is 0, U1 is 0.5 into 10 power minus 3 joules is equal to T2, which is 1/2, and the mass we have assumed to be what? Let's say it's 1 kilogram. So that's 1 times V2 squared. Okay, so that would be equal to V2 squared equal to 1 times 10 power minus 3. So all we have to do is take the square root of 10 power minus 3 meters per second. That will be the speed in configuration 2. Okay, let's do another example. On this example, what we'll do is we'll do actually an incline, and I'll have a barrier, and I'll have my block, which is tied to spring constant. Again, let's say we'll choose the same spring. That's 10 Newton per meter. So 10 Newton per meter. The mass M is equal to 1 kilogram. Okay, and now the question is, let's say we release it from rest. Okay, so this is the initial position, position 1, and we say that V1 is 0 in this position, and due to gravity it's free to slide in the downward direction. So if it has moved down by a distance of, let's say we'll call it 5 centimeter, the question is, what is the speed in position 2? Okay, so let's draw free body diagram in a generic configuration. So let's say generic configuration is here. What are the forces? We have Kx, we have mg acting downward, we have the normal reaction going that way, and assuming this is a frictionless surface, so we will not have friction over here, then we can see that all the forces that are doing any work are conservative and clearly will not do any work. Mg will do work because mg has a component that points along direction of displacement. If this angle is theta, this is theta, so this would be mg cosine theta. That will not do any work because it's perpendicular direction of displacement. This is mg sine theta. That will do work, right? So let me draw this again separately. So we have the block, we have the normal reaction, we have mg, this is theta. So this is, in this direction is mg cosine theta, and on this direction is mg sine theta, and then we have kx. Okay, so n does not do any work, mg cosine theta does not do work, kx does, and mg sine theta does. Okay, so both of them are conservative forces, which means we can apply T1 plus U1 equal to T2 plus U2. Initial T1 is 0 because it's released from rest. So what's U1? U1 here would be potential energy due to gravity as well as potential energy due to spring forces. Now, potential energy due to spring forces is defined as 1/2 kx1 squared plus the potential energy due to gravity is defined as mgy1. So this is 0 because initially it's not stretched. So what's y1? So to indicate y1, we have to choose a datum. So what we'll do is we'll pick our datum to be actually going through position 2. So that's my datum, a horizontal line. Okay, so now the question is, what is y1? Y1 is this vertical distance. Okay, so let me draw this triangle separately. So I have a right angle triangle. This is y1, and this is my datum, and this is theta. Okay, so if we know that this is 5 centimeter, then we can find out what y1 is. Okay, it's because sine theta is equal to y1 over 5 centimeters. So y1 is actually 5 sine theta in centimeters. So let's say theta is given to us 30 degree. So this would be 5 sine 30 which is 1/2, so that's 2.5 centimeters. Okay, so this would be equal to 1 times g is, let's say, 10 times y1 is 2.5 into 10 power minus 2 meters, so that's 25 into 10 power minus 2 meters, or this is 0.25 joules. Okay, so that's the u1. Now what is t2? T2 is 1/2 mv2 squared, which we don't know. We're looking for the speed. What is u2 here? u2 would be u2 due to gravity plus u2 due to elastic forces. u2 due to gravity would be 0 because our datum is actually going through position 2, right? So u2 due to gravity is mg y2, and y2 here is 0 because our datum goes through the position 2. What is u2e? That would be 1/2 k. K is given as 10 times x squared. So the stretch would be now 5 centimeter because that's the distance traveled. So that's 5 into 10 power minus 2 whole square. So that gives us what, 25? No, actually it's 125, right? 125 into 10 power minus 4 joules. That's u2. Okay, so all we have to do is now add them together, right? T1 plus u1 equal to T2 plus u2. T1 is 0, u2 is 0.25, T2 is 1/2, mass is 1, v2 squared plus u2 is 125 10 power minus 4. So let's do the math. What do we get? So we get v2 squared over 2 equal to 0.25 minus 0.125. So actually it's not 0.125, this is 0.0125. Okay, so that's 0.0125. Okay, so what do we get out of that? Let's do the numbers. So this is equal to 0.2375. So v2 would be equal to, let me multiply that with 2 and then do a square root finally, and I get 0.689 meters per second. That's the speed when it reaches configuration 2. Now let's do an example where we have some non-conservative forces. Okay, so let's do a third example. So example 3, I have a block and it's being pushed by some force F of 10 Newton, let's say. Okay, and there is friction force UK being 0.3. Okay, so we know the kinetic coefficient of friction between the two. The mass is given as 1 kilogram. Let's say G is equal to 10 meters per second squared. And the question is, let's say this is released from rest, initial velocity would be 0, so v1 is 0. Let's say, you know, it moves by a distance of, or let me change this problem slightly. I'll say that it has acquired a velocity at position 2 to be equal to, I don't know, let's say 5 meters per second. Then how much is the distance traveled by the particle? So if we apply our test, we can see that the test is positive. We are being asked to relate the velocities or change in velocities with the position changes. So potentially we can use the work energy approach. Now the next question is, can we apply conservation of mechanical energy principle in this case? So for that, we have to draw a free body diagram at an intermediate configuration. So let's say between 1 and 2, somewhere here, we'll draw the free body diagram. So we have the normal reaction, we have the weight, and then we have mu kn, which is our friction force opposing the motion, and we have our external force F of 10 Newton applied. Okay, so clearly N will not do any work, mg will not do any work because both of them are perpendicular direction of displacement. F will do work and mu kn will do work, right? So F and displacement are in the same direction, so that work done would be positive. Work done by mu kn would be negative because mu kn is pointing towards negative x direction while displacement is towards positive x. So let's say this is positive x direction. Okay, so now if we look at the forces, are they conservative? Mu kn is not a conservative force. F is an unknown force, so we cannot use delta T plus U equal to 0. Okay, so this is not valid here, so we cannot use conservation of mechanical energy principle. So what can we do? We go back to our original formula, which is that W is equal to delta T. Now this is the most general formula that we can always use. So here the work done would be due to friction force plus work done due to the external force F, and we have to compute those, and that would be equal to delta T. So let's compute work done due to friction force first. What would be that? That would be minus mu kn, and n is equal to mg, because in the vertical direction there is no displacement, times the distance traveled, that's delta x. Why is this negative? Because we know that the work done is defined as integral dw, which is nothing but integral f dot dr. In this case, f is pointing towards negative x, dr is pointing towards positive x. So if you do the dot product, the answer would be a negative quantity, right? That's something we have seen before. So we get W sub f. So what would this be? It would be minus 0.3, and this would be 1 times 10. So that's 10 times delta x. We don't know what that is, so we're looking for that. So this would be 3 times delta x with a negative sign in the front, and that's in joules. Now, what is the work done due to uppercase F, the external force 10 Newton? That would be nothing but, because it's a constant force, so it would be simply multiplication of the force itself times the displacement, so 10 times delta x joule. So if we add those two, what do we get? The total work done would be W sub F plus W uppercase F. That would be minus 3 delta x plus 10 delta x joule, so that would be 7 delta x joule. What about the right hand side? Delta T. What's delta T? Delta T is final kinetic energy 1/2 mv2 square minus initial kinetic energy, and this is 0 because v1 is 0, speed is 0. That's 1/2 times 1 times v2 is given to you as 5 meters per second, so that's 25, so that will be 12.5 joules. So let's equate that. So W is equal to delta T, so we get 7 times delta x equal to 12.5. So delta x will be equal to 12.5 divided by 7, and that comes out to 1.78 meters. So this is 1.78 meters. And that's the distance traveled by the particle when you have non-conservative forces acting.